Hello, and welcome back to AP Human Geography. Today I want to continue the conversation about primary activities. We've talked about gathering, which is things like hunting and fishing and harvesting, and now we want to shift to the extractive industries. So what we're talking about here is taking something from the Earth's crust, right? We're exploiting a natural resource found in the Earth itself, and so when we talk about extracting, we're talking about mining, quarrying, and drilling. And interestingly enough, right, like so many of the things we see, when we talked about agriculture, we're talking about you can only grow what will grow in your area, and you can do some modifications to your soil. You can build greenhouses, things like that. So you can force some things, but on a large scale, you can really only grow what'll grow. Well, this is going to apply also to the recovery of minerals. It's unevenly distributed because it's based on past geologic events. And so you really get what you get based on where you live, and this goes to everything. And so the labor forces in countries, right, are going to be determined by those basic sectors. Well, extractive industries are a basic sector, and so you will have areas that might be coal mining towns or gold mining towns or limestone quarrying towns, and it's all dependent on what they've got underneath them. And so when we talk about any of our resources, we can divide them up into the non-renewables, the renewables, and the reusables. When we're talking about metals and minerals and fuels, we have non-renewable, which means you use them one time and it's done. And then we also have reusable. This is different from renewable, right? And we'll talk about renewable and non-renewable again when we talk about energy in particular. But reusable means that you can recover it, and you can recycle it. All right, so let's talk about what we actually get when we are extracting. Really, it's divided up into four categories. You've got your metals, and I think those are pretty obvious. And then you have your non-metallics, and these are what we call minerals. This is going to be stuff like sulfur, lime, which is calcium carbonate, salt, that's where halite is there, gypsum, that's kind of what we make drywall out of, gems, semi-precious like turquoise, and precious stones like sapphires, emeralds, diamonds, things like that. Anything that's non-metallic that we find valuable that we pull out of the earth is going to be a mineral. Now we also have rock resources. These are the things like big building materials, so your limestone, marble, granite, also things like sand and gravel. We build road bases out of that. We also make glass out of quartz-rich sand. So lots and lots of things. Oh, if you like baby powder, the talc in that's mined, right? Things like that. Makeup, powder and makeup. Now, the fourth area is the mineral fuels. Okay. Now, the mineral fuels are going to be your fossil fuels, coal, oil, and natural gas, and also your fissionable materials, which are uranium and plutonium. And we will talk about those more in depth. These are all non-renewable. All of your metals are actually completely reusable because you just melt them down and do something else with it. A lot of your minerals can be recovered and reused, and then same thing with your rock resources. And if nothing else, you can recycle the minerals and the rocks too. So there's that as well. All right, your next question is, knowing all of the things that we know, extraction is responsible for which of the following products? Well, wool seems obvious. That comes from animals, right? Sheep in particular. Gelatin, you may or may not know, is also an organic product. It can be made from animals. It can also be made from plants. Historically, it's made from hooves, just as an aside. So that kind of leaves charcoal, plastics, and glass. Charcoal actually is made from a process of partially burning wood. So wool, charcoal, and gelatin are all animal products. Glass is made by melting sand. And a fun fact, you can actually get natural glass when lightning strikes a sandy area, a beach in particular. And that's kind of fun. You also get plastics from oils, right? So plastics and glass are both products of extraction. All right, so one of the things that's really important to think about is that geology matters. It is the geology of the area that is going to determine what kind of resource is available. So if you're talking about coal, for instance, and we will talk about that, or natural gas or oil, you're talking about large deposits of organic matter that's pressed under high heat and pressure into the products that we now use that have such high energy. But this is going to be true for everything. And my example for you today is going to be diamonds. Diamonds are made, they're just graphite, right? The same thing as pencil lead. It's just that they have been put under such high heat and pressure because of the volcanic activity. They come from a structure called a kimberlite volcano, and so you actually find them in what are called kimberlite pipes, which are the center of that old volcano, and they're made literally by explosions, right? Explosive forces. And so what you get are these like little smatterings of debris, right? But that debris happens to be diamonds, and this is a raw diamond, and this is a kimberlite pipe. So what that means is that when we're finding materials, we need to look for particular geologic structures and geographies that would tell you that that geology is there. So it's this combination of looking at the lay of the land and then what the land is actually made of. And so you do two things. You use GIS, right? So you use these overlay systems, these geographic information systems that we learned about in the beginning of class, and you get those by remote sensing. That remote sensing is then verified by ground truthing. And remember, ground truthing is really important because that is where you actually go to the area and see if what you want is there. And we do this for all kinds of things, right? Because just because you see something on the satellite, it's kind of like the face on Mars. There's not actually a face carved into the surface of Mars. Look it up later on Google, face on Mars. It just happens to be a series of canyons. When we see it, we see a face. No face there, right? So it's important to actually get on the ground to verify what you've seen. And then here's just another example where you can use false color images to kind of divide up. And then as you look at, okay, so this is a ridge line. Is that gonna, with this kind of rock, is that gonna give me what I want? Okay, so once we find it, how do we get it, right? So to remove large near-surface deposits of minerals, such as gold or copper, what would we do? Open pit mining, surface mining, quarrying, subsurface mining, or chemical extraction. So these are the 5 big mining types, right? And the answer to this happens to be open pit mining. So there are 4 kind of surface mining techniques and then 1 deep underground or relatively deep underground subsurface mining. So that's underground mining. But for gold and copper, we typically do what's called open pit mining, and this is what you were seeing when you saw in that kimberlite pipe, and I'm going to show you an open pit mine in just a second. Basically, we dig a giant hole in the ground, right, and then we pull everything up. Surface mining is usually a term that is really about coal mining, and that's where we cut strips into the ground and then we fill them in, and then we cut a strip and then we fill it in and cut a strip and fill it in. You can mine coal with an open pit, but in open pit you typically leave the pit open. In surface mining, you typically close the pit. Although people use those terms interchangeably, by the way, so you'll hear open pit mining and surface mining kind of interchangeably, but there's a subtle difference there. Quarrying is where we go in and we actually cut away large pieces of rock. Quarrying is all about getting rock resources. Surface mining is all about coal, and open pit mining is all about minerals. Now, chemical extraction is another method of mining where we actually kind of dig in, we flush chemicals into the surface wherever the reservoir of material is, we dissolve it out, and then we suck it back out. We actually mine uranium in Texas this way through chemical extraction. But this is something we are not going to focus on. Partly we're not going to focus on it because it doesn't change the geography of the land, and this is a geography course. And so what we really want to do is talk about the changes in geography, right? So when we talk about changes in geography, we are talking about 3 methods of mining that are really actually quite destructive. When you mine something, you have to take away the surface entirely. Now, in surface coal mining, we'll talk about that when we talk about energy. There is a big push in the United States, in particular, to recover the land and build the surface back up, and that's great. But that's not always the case in open pit mining. Usually what you have is a big pit that becomes a lake when it's closed, and these are huge. Just to give you an idea, this little black dot right here is this giant earth mover here, and this is a car, right? And you can see that's like an SUV. These are huge. These wheels are like 14 feet tall, and that is that, right? And so these are enormous areas. This guy right here, these things are about 300 feet tall. By the way, when these arms swing their buckets, the buckets come in and they scoop away the coal here. This is a coal mine, by the way. They can actually swing up to like 80 miles an hour because this arm is so long. And so, I mean, all of this stuff is on an enormous scale. This is mountaintop removal. Here are all your nice little ridge lines. Here's your not ridge lines. So we actually change the geography of the Earth's surface through our extraction processes, and as technology has increased, we have become more efficient at this. So we're talking about big stuff, changing the Earth's surface, all of these things. So you can see that there are some huge hazards associated with mining, right? This is a very dangerous job. But the most dangerous type of mining happens to be underground mining or subsurface mining. So what is the biggest hazard? This is also what we think of when we think of mines. We usually think of people going down into the earth in dark tunnels and pulling stuff out. And actually the most common mining is all going to be your surface, everything on the surface, the open pit, and the surface coal mining. Mountaintop removal, by the way, is illegal in the United States. It has been since the 70s. We haven't done mountaintop removal in a really long time. When we do that now, we do something called shaft mining, which allows us to go into the mountain as opposed to destroying the mountain. So just as a side note on how we've stopped doing some of the changes that we have. Okay, so back to the subsurface mining. This is the most dangerous kind of mining. What is the biggest hazard for subsurface mines? Ventilation issues, explosions, earthquakes, loss of electricity, or flooding? Now I just want to say all of these are problems. Obviously having ventilation problems, that's a huge problem, right? Because then you suffocate, and that does happen. Earthquakes, those happen. Earthquakes are happening all the time. Earthquakes can lead to mine tunnel collapses, and that's a real problem. Loss of electricity, probably not catastrophic, but all of a sudden you're plunged into darkness, none of your pumps work, this is bad. But really the least of the 5 problems. And then flooding, that's sort of self-explanatory. If you have a pocket of water or groundwater starts to seep in, that can be a huge issue. The biggest hazard, though, to underground miners are explosions. Is there pockets of gas, they're flammable things down there, and a little spark can actually ignite them. And ventilation issues are caused by some of these gases. There's a lot of gas pockets down there. It's why they used to send canaries into the coal mine, right? Like the canary in a coal mine, that phrase comes from it actually sending little birds in. If the little birds survived, it was safe for miners. If the little birds didn't, then they had to do something to flush out the gases. But back to these explosive gases, explosions happen, they cause loss of life from the explosion itself, but also they start collapsing tunnels because the force of the explosion, and this is a secondary problem. So explosions are really the most dangerous thing that you have in subsurface mining. All these are problems though. Okay. So how do we determine when to mine and why? First of all, it's about world demand and the available market, right? It's about energy. How much does energy cost? It's about labor. How much does it cost to do it, right, would be energy and labor, right? Because you need a lot of energy to mine and you need a lot of labor to mine. So these are probably the most expensive parts. And then how far are you going to need to take it so it's processed? How far do you need to take it to sell it? That's always part of the cost. Then in developed nations, there's the environmental cost. Remediation is really expensive. You have to, at least in coal mining, you have to leave the land better, as good or better then you found it, and that's tremendously expensive, and they do an excellent job at it here in the US, but it's very expensive. And then also, how much are you going to get out, right? Because it's whatever you pull out of the ground is where you're going to make your money. So you have to be able to pay for all of the stuff, right? The energy, the labor, the processing and selling, and the environmental cost, plus make a profit, so you can keep doing it. So these are all the cost factors. And it turns out that we actually use a lot of mined products. So when you start thinking about, this is just a small amount of the stuff that you will use in your lifetime, or the average American will use. But it turns out to be about 3.1 million pounds of minerals, metals, and fuels in a person's lifetime. That is huge. When you think about it, every year you've got new minerals. So that includes the recyclable minerals, but what about new minerals? Lots and lots of things. So take a look at these two slides, get some examples of the kinds of things that go into your life that are from extractive industries. And the US is mineral and metal rich. We have lots and lots of mines, and these are just our surface mines. And we're not the only one. China, right, consumes a huge amount of raw minerals. And so when you start looking at their usage, they're almost on par with us, right? And so the developed world and rising countries of rising affluence are using more and more raw materials, which is one of the reasons that reuse and recycling, reducing, reusing, and recycling are so important when you think about that. And then remember that most of these things will run out at some point. Most of these things will run out at some point. Some of them can continue to be used, right? But as the population grows, each person has a smaller share. So whatever's happening, we're looking at decreasing supplies in the future. Okay, so that's a little bit about the extractive industries themselves. From primary activities, right, we start very simple, just sort of digging things out of the surface, collecting off the surface, basic fishing, basic harvesting, all of those things. But over time, technology changes the way that we live our lives. So your next question is, what exactly is technology? Is it just making life simpler with stuff? Or is it designing sophisticated devices that can accomplish both simple and complex tasks for us, using knowledge to develop products and systems that satisfy needs, solve problems, and increase our capabilities, solving problems with the assistance from a device or tool that allows us to view the problem from a different perspective, or that gives us access to a greater skill set, or none of these? When we think of technology, we think about like sophisticated stuff, right? But it turns out that it's really just using knowledge to develop products and systems that help us. So that's number 3. So when we think about technology, we can divide it up into these technological eras, really from like the Stone Age to the modern age. And so we start looking at our technological eras basically with the agricultural era, right? And so we start there. We're thinking about 10 to 12,000 years ago, and then everything before that is like Paleolithic, right? Or prehistoric, yeah. So agricultural era, that can be divided up in the Stone Age, Copper Age, Bronze Age, and Iron Age. And what you're looking at are the technologies that we've developed to change the stuff that we're using to make it better. And it's as we're able to extract more, as we're able to harvest more, we get big shifts. We then move into the industrial age, then the information age, and the communication age. And in the industrial information communication age, we also have the nuclear age. So there's some overlap in these technologies, because we could also look at in terms of like when the medical age begins, right? So there's all kinds of quote ages. We're just going to focus on the ones that deal with the extractive industries. So ultimately, we get better technology because we're able to build on what we have learned in the past. So when we start with the Stone Age, that's going to be up to about 3500 BC, right? Basically, we traveled around in nomadic groups. We made tools from stone that were relatively simple, sophisticated, but relatively simple. We went from gathering wild plants to planting, and that is really the hallmark, right? In the late Stone Age, we start to collect native metals. These are things that we can basically see, right? Gold you can actually see in rivers, you can pick it up. We're using stuff that's really soft, it's really malleable. It's also fairly rare, which makes it valuable, so we start to have this kind of shift to having things that are more exclusive, things that we can assign wealth, right, to. Yeah, so this idea of wealth. We're also beginning to see the use of copper, right? So this is about 4500 BC to about 3500 BC. There's a considerable overlap because it kind of depends on where you are as to who's doing what. But we're using stone and we're using copper. Stone is actually harder, right? Copper's very soft. And so we used it for making objects that are difficult to make with bone or stone, but it doesn't actually really replace bone and stone for stuff, and you have to be able to process it, right? You have to be able to pull it out of the ore, and metals and a lot of minerals hang out with other rocks, and so like you'll see gold is flecked inside stone. That stone that holds the mineral you want is called ore, right? Now, so occasionally we get iron and nickel that occurs in meteorites, but that's really, really rare. So we're using really copper up until about the Bronze Age. And bronze is an alloy of copper and tin. An alloy is where you mix two metals together, and what you get there is this combination of the qualities of both of those things, right? So this is about 3500 to 1200 BC. Still pretty soft, tin's a little bit better, and it can be molded, and that's great. Now, some other developments that happen at the same time, we get yarn and fabric, so weaving, we get irrigation systems, and we get carts with wheels. Remember, the invention of the wheel changes the world? Yay! Okay, now we move from the Bronze Age into the Iron Age, and this really shifts everything, okay? This is from about 1200 to about 500 BC. We have been able to build better furnaces, and so this allows us to melt down iron. It's called smelting. It's getting the impurities out, making it pure iron. So we get some really big advances here. We get iron-tipped stuff like plows, which allows us to cut into the ground better. We get better weaponry, which is something that we'll talk about. Some other developments that occur in this time are going to be general new building techniques. We have this huge advancement in how we build things because of these tools. We also get ocean-going boats, and we start to have big road systems to match our growing trade systems. Now, here's the thing about iron, though. It's not ideal. It's actually softer than bronze, and it doesn't hold an edge unless you harden it. And hardening it means that you have to heat it up and cool it down and heat it up and cool it down. It can be brittle and break easily if you don't do this well. If you do it really well, then that hard edge is like really hard and really useful. If you don't, it breaks a lot. It also tends to oxidize, which we call rust, and rust eats away at the metal and makes it weak. It already has that tendency to be brittle, so those two things don't go together. So there were two really big advances, right? That hardening the metal that I told you about, that's called tempering. You can do it to lots of things. We temper glass too, so if you think about Pyrex, that's actually tempered glass. But this heating and cooling causes it to get really hard. The other thing that we do is we turn it into steel. Steel is iron that has carbon added to it, and that makes it a lot stronger, right? So the idea of carbon steel. Steel and coal was actually the backbone of the Industrial Revolution, which brings us the Industrial Age, and steel is still one of the most important metals in today's society. So the Industrial Age is about 1750 to the early 1900s. We start seeing sophisticated machines. We get new power sources because we've also discovered coal and oil at this time. We start to see this urban shift, people moving from agrarian societies into the cities, and this is really important. The Industrial Age is a huge shift for us. Now, there are some new and there's some improved industries. Textiles, because we now have mass production and assembly lines and things like that. Textiles, chemical manufacture, transportation, communication, advances in metallurgy and mining, and then, of course, the making of paper on a mass scale. So these are all really important developments in the industrial age. Now, the next thing that we see, early 1900s to the early 1990s, is the information age or the digital age. And the really big development here does have to do with extraction, but it has to do with oil byproducts, and that is plastics. Plastics change the world, and these new technologies lead to all kinds of things. Plastic helps us develop computers and transistors, and those are both really important. Transistors are really important to all kinds of electrical stuff, including computers, and computers, that's pretty self-explanatory. So there's lots of new manufacturing technology that comes up, and because of developments like steel and these fossil fuels, we get a lot of increased travel, also with those great road systems. So information access and exchange becomes a lot quicker and easier. Think telephone all the way to internet, right? Now, we're in the communication age. So this is where we have all of this technology, really sophisticated technology, at our fingertips. Almost every person has access to these really, really amazing high-powered devices. Your phone is significantly better than computers have been historically, right? It's amazing. And the communication, so we'll be talking about how this instant mobile communication has been another basically equivalent of the industrial age in terms of societal changes. We'll talk about that later on. But getting back to technology, now that we're in the communication age, we have something called Moore's Law. Gordon Moore was a co-founder of Intel, which is a big computer company, and he said that essentially technology and its capabilities doubles about every 18 months. And so one of the questions that's been asked based on this is, are we now using technology that has far outpaced our ability to actually handle it? That's a really good question. All right, last thing we want to talk about is the nuclear age. The nuclear age begins in the 1940s, and it goes along with a lot of those technology changes, but this is kind of considered its own sort of age. So we live in multiple ages, if you think about it. Because we have this discovery in uranium and its ability to fission, and then the subsequent making of plutonium through uranium fissioning, which also fissions. Both of these produce massive amounts of power, previously unimaginable power, and clean electricity. We'll kind of define that later on. Not today. But it leads to this ability to produce large amounts of electricity, and this is phenomenal. It takes pressure off of coal, takes pressure off of oil, right? We can do all sorts of things, and not oil, sorry, natural gas, takes pressure off natural gas, and this is great, right? It also means that we can harness that power, that immense power, into weapons of mass destruction, and I'm talking about nuclear bombs, atomic bombs, right? Hydrothermal bombs. So this is a huge impact on the way that we now view life and society because of this previously unknown ability to destroy. And this is another question: how has this changed us? The nuclear age also changed our society, which we will talk about later on. Okay. That is it for today. We've sort of walked from Stone Age all the way up to the modern age, and how that's impacted the primary industries, what the primary industries are, or primary activities rather are. So if you have any questions, please ask in class, and I will see you next time. Thanks for listening.